Welcome to the video lecture on improper integrals. The definition of a definite integral from a to b of f of x dx requires that the interval from a to b be finite. The fundamental theorem of calculus requires that the function f of x is continuous on the interval a to b as well. In this section, we are going to learn how to evaluate integrals if these conditions are not met. So for example, if one or both of the limits of integration are infinite, or if the function has a finite number of infinite discontinuities in the interval a to b. An integral of this type is said to be an improper integral. Examples of integrals that have infinite integration limits would include the following. So the integral from 1 to infinity of 1 over x squared, which would have this graph, and that would be like imagining the area from 1 up to infinity, so that sort of infinite region right there. The second example has an infinite limit in the lower bound from minus infinity to negative 1, so that would be the infinite area from negative infinity up to negative 1. And then this third example has two infinite bounds from minus infinity to positive infinity, so that would be the area underneath this curve all the way to the left and all the way to the right. So to get an idea of how to evaluate an improper integral with an infinite limit, such as the integral from 1 to infinity of 1 over x squared dx, consider the integral from 1 to b of 1 over x squared dx. This integral can be interpreted as the area of the region between x equals 1 and x equals b. So if you draw that, that's just going to be this area from 1 up to b. And that's a finite area. So we can find its area by finding the integral from 1 to b of 1 over x squared. And to do that, we just integrate. I'm going to think of that 1 over x squared as x to the negative 2. When you integrate x to the negative 2 and you add 1 to the power, it becomes x to the negative 1 over negative 1. And if you rewrite that, that's negative 1 over x from 1 to b. So if I plug in b, I'm going to get negative 1 over b minus, if I plug in 1, negative 1 over 1 is negative 1. The minus minus becomes plus, so this is negative 1 over b plus 1. Now what happens to that answer as b goes to infinity? Well, 1 over infinity blows up, the b blows up and 1 over infinity goes to 0 and gets smaller. So this is going to go to 0, which means 0 plus 1 is going to go to 1. So the value of this integral becomes 1 as b gets really, really large. So this improper integral can be interpreted as the unbounded area between 1 over x squared and the x-axis. And it would just look like this area starting at 1 and going all the way to that x-axis, getting smaller and smaller and smaller. And what we just showed is that that area is actually finite and it goes to 1. So what we're going to do to deal with these improper integrals is turn them into limits, and we're going to take any infinite bounds that we have and turn them into limits. So for example, if you have an upper bound that goes to infinity, then we're going to swap that out with a b and let b go to infinity and find this integral here, and then take the limit of that answer as b goes to infinity. If the lower bound is minus infinity, then we're going to swap that out. You can pick whatever letter you want here. I chose a, and if I want to find this integral, I'm just going to take the integral from a to b and then take the limit of that answer as a goes to minus infinity. Now, if both of your bounds are infinite, then what you're going to have to do is find a number, any number, doesn't matter what, that's in between minus infinity and infinity, and we're going to break this up into two different integrals. So I chose c, and I went from minus infinity to c plus the integral from c to infinity. And then for each of these, you would have to change these two limits. So this one would be the limit as a goes to minus infinity of the integral from a to c, and this would be the limit as b goes to infinity of the integral from c to b. Now in the first two cases, the improper integral converges, that means it exists and has a value, if the limit exists. Otherwise, we say that the improper integral diverges. In the third case, we say that the improper integral on the left diverges if either of these two integrals on the right diverges. So if either one of these is infinite, then the original one is infinite. So an example here, the integral from 1 to infinity of 1 over x dx. So what we're going to do is we're going to think of this as an area. We're going to change that upper bound of infinity to a b. So I'm going to make this the integral from 1 to b of 1 over x dx, and then I'm going to take the limit of that as b goes to infinity. So 1 over x looks something like this. So from 1 to b would be this finite area right here. So let's find out what that would equal. Well, what's the antiderivative of 1 over x? Well, that's just the ln of x from 1 to b, and I'm going to plug in those bounds, and then I'm going to take the limit as b goes to infinity. So if I plug in b, then this just becomes the ln of b, and b is positive here, so I can drop those absolute values. If I plug in 1, the ln of 1 is 0, so I'm just subtracting 0. So what happens to the ln of b as b gets really, really big? Well, the ln of infinity is also infinite. So this goes to infinity, which means this limit doesn't exist. Therefore, this integral does not exist, and we say that the integral diverges. So the integral from 1 to infinity of 1 over x dx is divergent or diverges. What about if we have the integral from negative infinity to negative 1 of 1 over x squared dx? So this looks pretty similar, but it's going in the other direction now. We have a slightly different function, and this time we're going to the left towards minus infinity. So let's chop it off. I'll call this a, and find the area from a up to negative 1. So I'm swapping out that minus infinity with an a, and then I'm going to take the limit of that as a goes to minus infinity. So first let's change this 1 over x squared to an x to the negative 2. When I add 1 to the power, that becomes an x to the negative 1 over negative 1. And if I rewrite that as negative 1 over x, then when I plug in my bounds, when I plug in negative 1, I'm going to get negative 1 over negative 1, which is 1, minus the limit as a goes to minus infinity of negative 1 over a. So as a goes to minus infinity, again, that's in the denominator. So if the denominator is getting big, then the fraction is getting small. So this is going to go to 0. So now we have 1 minus 0, which is 1. If you get a finite answer and that limit actually exists, then that means this integral exists and it's equal to 1. So that means that this converges, this improper integral converges, and that means that this is actually a finite area that equals to 1. And it's the fact that this x squared has a higher power, which is making this integral converge, as opposed to this one up here, which was just an x to the first. That wasn't a strong enough power to make this area be finite. Okay? Now if we take a look at this one, from minus infinity to infinity, this time both of our bounds are infinite. So on this one you have to be very careful. The proper notation is to split this up first before you even introduce any limits and chop it up into two separate integrals. So I'm just going to pick any number that's between negative infinity and infinity, like 0, and use that as my breaking point. So this becomes the integral from minus infinity to 0 of 1 over x squared plus 1 dx, plus the integral from 0 to infinity of 1 over x squared plus 1 dx. You need to get that finite bound in there that actually does exist and is continuous. Once you have that bound in there, then the infinite bounds you're going to swap out and turn those into limits. Doesn't matter what letter you pick. For this minus infinity, I'm going to use a and let a go to minus infinity from a to 0 of 1 over x squared plus 1 dx, plus for this positive infinity, I'm going to choose b and let b go to positive infinity from 0 to b of 1 over x squared plus 1 dx. Now the good news is that these are the same integrals, so they have the same antiderivative. So for this first one here, if I want the antiderivative of 1 over x squared plus 1, you need to recall and remember that that's an arc tangent. So the antiderivative of this is going to be the inverse tangent of x. Our a squared is just a 1, so we don't need any extra coefficients. And that's going to be the same for both of these. So now I'm ready to plug in my bounds. When I plug in 0, this is going to be the inverse tangent of 0 minus the limit as a goes to minus infinity of the inverse tangent of a. And then for the second one, I'm going to get the limit as b goes to infinity of the inverse tangent of b minus the inverse tangent of 0. So inverse tangent of 0 means what angle when you take the tangent of it gives you 0. And remember, tangent is sine of x over cosine of x. So tangent is going to be 0 when sine is 0, which is at 0. So this is 0 and this is 0. Now for these two with the infinities, let's plug them in. We're going to want to know the angle that when you take the tangent of it, it's going to go to minus infinity. That's essentially what we're doing. We're plugging in minus infinity for that a. So we need to know when you take the tangent of some angle, what angle does it take for this to go to minus infinity? And you might need to recall the graph of tangent of x. This is sine of x over cosine of x. And that fraction will blow up and go to infinity or minus infinity when that denominator is 0. And cosine is 0 at pi over 2 and minus pi over 2. So tangent looks kind of like this, where you have those vertical asymptotes at the multiples of pi over 2. And for the domain of inverse tangent, in the range you get your angles between minus pi over 2 and pi over 2 only. So what angle when I take the tangent of it is going to make tangent blow up to a minus infinity? Well, that's going to be negative pi over 2. And we want the minus in front of that, so this becomes positive pi over 2. When I look at the positive infinity here, we're looking at what angle when I take the tangent of it makes the tangent blow up to positive infinity, and that's going to be positive pi over 2. And again, the reason for that is because tangent is sine over cosine. So sine of pi over 2 is 1, but cosine of pi over 2 would be 0. So that's going to blow up to positive infinity. Whereas sine of negative pi over 2 is negative 1 over cosine of pi over 2, which is 0. So that's going to blow up to minus infinity. So for this one, we got minus pi over 2, but it became plus because of the negative in front. And for this one, we got pi over 2, which stays plus, and pi over 2 plus pi over 2 is just pi. So we got a finite value. The limits existed, which means the original improper integral converges and has as its area pi. So that infinite area is actually pi. Okay? Okay, on this next example, we want to integrate from minus infinity to 0 x e to the 2x dx. So the first thing we want to notice is that we have that infinite bound in the bottom. So we're going to want to swap that out. So I'm going to use the letter a for that and take the limit as a goes to minus infinity of the integral from a to 0 of x e to the 2x dx. Now to actually find the antiderivative of this, notice that we have a power of x times an exponential function. And that product makes it an ideal candidate for integration by parts. You could also use integration tables, but as a review, I'm going to use integration by parts, and I'm going to let my u be the x and the rest of it be dv. So dv is going to be e to the 2x dx. So therefore my du is just the derivative of x, which is 1 times dx, and the integral, I need to be a little bit careful on here. In order to integrate e to the 2x dx, notice that that is e to the stuff. And in order to integrate e to the stuff, you need to have stuff prime present. And the derivative of 2x wants to be a 2. So we would need to have a 2 inside the integral. So we have to counterbalance by a 1/2. And the integral of e to the stuff is just e to the stuff. So this will be e to the 2x back again times that counterbalancing 1/2. So v is going to be 1/2 e to the 2x. So now that means over here we're going to get the limit as a goes to minus infinity, and our integration by parts formula is going to give me u times v. So we're going to get that x times our 1/2 e to the 2x minus the integral of v du. I'm going to pull the 1/2 out, and I'll have that e to the 2x and the dx left over. And I want to do this from a to 0. So now we want to finish off that integral, and what we notice is that it looks just like our e to the stuff again, and in order to integrate that we're going to need stuff primes. So we need to put in that 2, counterbalance by another 1/2, a 1/2 and a 1/2 out front becomes a 1/4, and the integral of e to the stuff is e to the stuff back again. So we'll get e to the 2x back again. And my bounds here are a up to 0. So if we plug in our upper bound of 0, this x becomes 0, so this whole term goes to 0, minus e to the 0 is 1, so this will just be that minus 1/4. And then we're going to plug in our a, so we'll get 1/2 a e to the 2a minus 1/4 e to the 2a. And now we're ready to try and figure out what this limit is going to become. So we get our negative 1/4 out front, and then when we go and we try to plug in this minus infinity, notice that this a is going to become a minus infinity, and this e is going to become an e to the negative infinity. Now e to the negative infinity is like an e to the infinity in the denominator, and e to the infinity is infinite. So this is acting like infinity over infinity, which is one of our indeterminate forms. So in order to evaluate this, we're going to need to figure out how to come up with its limit by using something called L'Hopital's rule. So let me go ahead and go over here and write out a little scratch work using L'Hopital's rule on this limit. Now, L'Hopital's rule can only be applied if you have a limit that's in the form infinity over infinity or 0 over 0. And in order to get this infinity over infinity, I had to move this e down to the denominator. So let me go ahead and do that here. I'm going to leave the a in the top, and the 2 and the e to the negative 2a are now going to be in the bottom. Notice I had to change that power to a negative to move it down. So this is going to give me that infinity on the top and that e to the positive infinity on the bottom, which is also infinity. So this is acting like infinity over infinity. So it does fill in the requirements of L'Hopital's rule of being in the correct form, either infinity over infinity or 0 over 0. So now we apply L'Hopital's rule by taking the derivative of just the top over the derivative of just the bottom. Don't use a quotient rule, just do derivative of the top, which would be 1, over the derivative of the bottom. Now the derivative of the bottom is going to give me the derivative of e to the negative 2a, which is e to the negative 2a back again, times a negative 2 times this 2 that's already there. So that's going to give me a negative 4. So now, hopefully, when I plug in my minus infinity, I won't get one of these indeterminate forms anymore. I'll get something that I can actually evaluate. So let's plug in our minus infinity. The top is now 1, and the bottom is just going to be that minus 4, and then we're going to get a negative 2 times a negative infinity, which is e to the positive infinity, which again is just something really, really large, something infinite. And it's going to be negative, but it's in the bottom. So 1 over something really, really big is going to get really, really small. So this is going to go to 0. So that's this. This part goes to 0. Now let's take a look and see what this limit does. So if we take the limit as a goes to minus infinity of 1/4 e to the 2a, if I plug in that negative infinity, we're going to get 1/4 e to the minus infinity, which again you can move down to the denominator, which means e to the positive infinity stays large, but it's in the denominator, so this is also going to go to 0. So both of these limits exist, and they both go to 0. So these are both going to give me a limit of 0, which means the overall answer here is going to be negative 1/4. And the fact that that actually exists and is a finite value means that the original improper integral converges and has an area equal to -1/4. Okay, so let's try another example very similar to this. Same bounds, almost the same function, but this time we have an e to the -2x inside of our integrand. So first thing we want to do is change that lower bound and swap it out. So I'm going to change this to the limit as a goes to -infinity of the integral from a to 0 of x e to the -2x dx. And we're going to use that integration by parts again to integrate this. So I'm going to let u be x, and dv is going to be e to the -2x dx. So du will just be dx, and v here is the integral. We need that stuff prime in there, remember? So we're missing a -2 in order to integrate this. So we'd have to counterbalance by a -1/2. So the -1/2 stays put, and we get that e to the stuff back again. So this antiderivative becomes u times v, so x times -1/2 e to the -2x, minus v, which is going to turn this into a +1/2 times the integral of v du. So this becomes e to the -2x dx, again from a to 0. So integrating that leftover integral, I'm missing my stuff prime, which is that -2, so I need another -1/2 out front to counterbalance. So this becomes a -1/4, and I get e to the stuff back again. And now I can plug in my bounds of a and 0. So if we plug in 0, this first term has an x in it, which is going to go to 0, so that whole first term goes to 0, minus e to the 0 is 1, so we're going to get that 1/4 again, minus the limit as a goes to -infinity of -1/2 a e to the -2a minus 1/4 e to the -2a. So let's just do a little bit of scratch work on this whole limit. Let's just go ahead and do it all at once. So if I take a look at this initially, we have that our a is going to -infinity, so -2 times that is going to make it become +infinity. So this is going to be an e to the infinity here times an infinity out front for that a, and then this one is also going to be an e to the +infinity with some constants out front, which aren't going to matter in terms of the size of these infinities. So e to the infinity is infinity, so this is infinity times an infinity, which is infinity, and this e to the infinity is also infinity. And what we end up with, because of the signs here, is we get our infinity right here, which is actually positive because we had a -1/2 times a negative infinity, which makes this become plus. So this is a positive infinity minus an infinity. That's another one of these indeterminate forms, because infinity minus infinity is not necessarily 0. It could exist. So in order to evaluate this limit properly, we can't just plug in our -infinity. That doesn't give us an actual answer. We're going to need to use that L'Hopital's rule again. So I'm going to erase what I have here, and I'm going to tackle this using L'Hopital's rule. And in order to use L'Hopital's rule, I need to convert this into either 0 over 0 or infinity over infinity. So my strategy is to try and get a fraction out of this. And what I can notice is that I have two terms here that have some GCFs. So let's pull out a negative and a 1/4, and they both have an e to the -2a. So let's pull out all of that. So from this first term, I'm going to have a +2 left, since -1/4 times 2 is -1/2. I'm also going to have the a left, but this e term is gone. And then for the second term, I'm pulling out all of this, so the only thing that's left is a +1, and it's going to be plus because I'm pulling out the negative as well. So by doing a little bit of factoring, then I can take these two terms in front and I can move them to the denominator. So I'm going to get a minus 4 and an e to the positive 2a in the bottom. Now let's plug in our negative infinity and see what we get. So 2 times negative infinity will be negative infinity, and the plus 1 is insignificant. On the bottom, we're going to get a negative 4 times e to the negative infinity. 2 times negative infinity stays negative. Now that e to the negative infinity, I'm going to move up. So it's going to become an e to the 0. Sorry, an e to the infinity. Sorry about that. And so then what we're going to have is a negative infinity on top times an e to the positive infinity on top, which is still infinite, over our negative 4. So this is acting like an infinity times an infinity, which is still infinity. Positive or negative really doesn't matter. So we don't actually have to use L'Hopital's rule here, because when you plug in, after you do a little bit of manipulating to turn this into a fraction, and you plug in that minus infinity, it's not one of our indeterminate forms anymore. It's actually just infinite. So this whole limit is an infinite limit, which means it doesn't exist, which means this whole thing doesn't exist, which means this diverges, and the original improper integral diverges as well. All right, if we look at this next example, this one's a little bit different because it has the sine of x in it. We still have that infinite limit on top. So right off the bat, be proper with your notation here. We need to swap it out. I'm going to turn it into a b and let b go to positive infinity, and this is going to go from 0 to b of sine of x dx. And that's pretty easy to integrate, right? The antiderivative of sine of x is a minus cosine of x. And we have bounds from 0 to b. So if I plug in my upper bound, that's just going to be negative cosine of b. And if I plug in 0, cosine of 0 is 1. So this becomes negative 1. So this is minus minus, or plus a 1 on the side. Now we need to figure out what the limit of cosine of b is as b goes to infinity. Now to figure that out, think about the graph of cosine graphically. Cosine of x just looks like this. And as x gets really, really large and goes to infinity this way, what's happening to these y values? Well, are they converging to a specific finite value? No, they're oscillating back and forth between negative 1 and positive 1. So the fact that this is oscillating back and forth infinitely often between negative 1 and positive 1 means this limit doesn't exist. It doesn't approach a finite value. So this limit is d and e, which means that this whole integral here must diverge because the limit doesn't exist. Okay? Now the next thing we're going to talk about is how to handle improper integrals that have an infinite discontinuity somewhere over the interval that you're integrating with respect to. So if you have a function that's continuous on an interval from a to b, so it's not continuous at one of the endpoints b, then what you can do is swap out that b and change it to a number c and take the limit as you approach b from the left-hand side, and proceed just like we've been doing with these previous examples. If that limit exists, then this improper integral exists. If that limit diverges, then so does the integral. If you have a lower bound, which is an infinite discontinuity, then swap it out and take the limit as you approach that lower bound from the right-hand side. If that exists and converges, then your integral converges. Otherwise, it diverges. And then finally, if you have an interval from a to b where somewhere inside of it there is an infinite discontinuity, then what you need to do is break up this interval from a to b and break it up at that point where there's a discontinuity. So it would be from a to c plus c to b, and then each of these integrals you would have to use this kind of limit notation for. If either of these two integrals does not exist because the limit doesn't exist, then this integral would not exist and would diverge. So for example, if you want the integral from 0 to 9 of 1 over the square root of x dx, there's no infinite bounds here. What the issue is that at 0, this function does not exist. It has a vertical asymptote. can't plug in 0. So 0 is the troubling bound here. So what we're going to do is we're going to swap it out. I'm going to call it C. And when I go on the interval from 0 to 9, I'm only using positive values there. So I'm going to approach 0 only from the positive side. And this new integral becomes from C to 9 of 1 over root x, which I'm going to change to x to the negative 1/2 dx. And now we proceed like we've been doing. The antiderivative of x to the negative 1/2, when I add 1 to the power, it becomes a positive 1/2 with a 2 out front. And if you want, you can swap that out and turn that into a square root. If you like to visually see that, this is 2 root x from C to 9. So if I plug in 9, the square root of 9 is 3. 3 times 2 is 6, minus, I'm going to plug in my c and get 2 square root of c. And we want the limit of this as c approaches 0 from the right-hand side. And here you do need that right-hand limit because this would not exist if we were coming through the negatives, because the square root of negatives don't exist. So we do need that right-hand limit here. And because c is just a square root function, we're able to just plug in that 0 and know that this limit, 2 times square root of 0, is going to just go to 0. So this is 6 minus 0, or 6. So 6 is the value of this integral, and it converges as well. On this next example, what is the trouble? We've got 1 over the cube root of x plus 1. So look at those bounds. They aren't infinite, but negative 1, if you were to plug it in, is going to make this denominator 0. So that's the issue here. So what we want to do is swap it out, change it into a c, and we're going to take the limit as we approach negative 1. And this time, negative 1 to 0, that's the right-hand side of negative 1. So we're going to take a right-hand limit from c to 0, and I'm going to change this to x plus 1 to the negative 1/3 dx. So the antiderivative of that, when I add 1 to that power, it becomes a 2/3 power with a 3/2 out front. So when I plug in 0, 0 plus 1 is 1, 1 to the 2/3 is 1, times 3/2 is 3/2. Minus, if I plug in c, I'm going to get 3/2 c plus 1 to the 2/3, and I'm taking the limit of that as c goes to negative 1 from the right. So negative 1, if you were to plug that in, negative 1 plus 1 would be 0. 0 to the 2/3 stays 0. So this whole thing does end up going to 0, which means my overall limit does converge and is equal to 3/2. Okay, now on this one, be careful, because initially it might not look like there's any problems and you might just try to integrate right away, and you'll get yourself in trouble, because even though we don't have infinite bounds, and neither one of these bounds makes this become undefined, if you think about x to the negative 4/3, that's 1 over x to the 4/3, and that denominator becomes 0 at 0, which is inside of this interval. So there's a discontinuity inside of my interval, which are over my bounds. So what I need to do is break up my bounds to include that discontinuity so that I can deal with it. So first thing we want to do before we even introduce any limit notation is break up this interval and make it negative 1 to 0 plus 0 to 1. And it's the 0 that's bad for both of these. So I'm going to swap out the 0 with a value. So here, let's just call it c. And when I'm going on the interval negative 1 to 0, that's the left side of 0. So this is a left side limit from negative 1 up to c of x to the negative 4/3 dx. And this one here, from 0 to 1, is the right side of 0. So here I'm going to use a right-hand limit from c to 1 of x to the negative 4/3 dx. Now the integral of x to the negative 4/3, when you add 1 to that, that becomes x to the negative 1/3. And then I multiply by the reciprocal, which will be negative 3. So if you want, you can clean that up and flip it around a little bit. This is negative 3 over the cube root of x. So that's what I'm going to be plugging my bounds into. So negative 3 over the cube root of x from negative 1 to c, and negative 3 over the cube root of x from c to 1. So if I plug in c on top, this is negative 3 over the cube root of c minus, if I plug in negative 1, the cube root of negative 1 stays negative, so this is negative 3 over negative 1, which is positive 3. And then if I plug in 1 into this expression here, negative 3 over the cube root of positive 1, the bottom is positive, so negative 3 over 1 is negative 3. Oops, I don't need my limit in there for that one, but I do need it for this second one. So when I plug in c down here, we'll need to take the limit of that. So when I take this limit here, the denominator is going to a 0, which means the fraction is going to blow up. If your bottom is getting small, then the fraction as a whole gets big. So this is going to some kind of an infinity. But we need to be careful about our signs. We're going through the negatives, and the cube root of a negative stays negative. So this will be a negative over a negative, which means this is a positive infinity. The signs are important here. If I go to this one over here, and I plug in 0, again, the bottom is going to 0, so the fraction as a whole is going to blow up to an infinity, but the signs are important. The bottom is going through positive, so this will be plus zeros on the bottom, over or underneath a negative, so negative over a positive stays negative, but there's this subtraction out front, so this actually becomes plus. Now it's actually good news that both of these are positive, because if you have a positive infinity plus a positive infinity, that's just going to stay infinite. And so that tells me that this whole thing is infinite, which means it diverges. If we had gotten an infinity minus an infinity, that would have been one of those indeterminate forms, which would have required using L'Hopital's rule to explore that limit a little bit more closely. So you have to be careful with your signs on those infinities, and if they're the same sign, you're in good shape. If they're opposite signs, then you've got to do more work. Now on this next example here, right away you'll see that you've got that infinite bound, so that's a trouble spot right there. But the other issue that you might overlook, and you want to be careful on these improper integrals, is the fact that this does have a denominator that will become 0 at negative 2, which is inside of this interval. So before you do anything else, chop up this interval to include that negative 2 so that you can deal with it. So this is going to be minus infinity to negative 2 plus negative 2 to 0. Then when you look at this first one, this is really bad news, because you have an infinite bound, which requires a limit, and then you have a discontinuity, which requires a limit. So these are both bad, which means you need to break this one up as well, which again seems a little tedious, but to be proper, you do need to make sure that you break this up so that at least one of the bounds is always something that is defined and does exist. So what I'm going to do is pick any number that lies between negative infinity up to negative 2. So let's just pick negative 3. Then what I can do is break this up into the interval from minus infinity to negative 3 plus negative 3 up to negative 2 plus negative 2 up to 0. So in the end, all of these are combining together to that original interval, but we're breaking them up so that at each of these integrals, at least one of the bounds is defined, and the other one we're going to convert to a limit. So in this first one, the negative 3 is okay, but the minus infinity is not. So let's make this the limit as a goes to minus infinity of a to negative 3 of 1 over x plus 2 dx. For the middle integral, the negative 2 is the bad point. So let's take the limit as c approaches negative 2, and we're coming from the left side of negative 2 when we're going from negative 3 to negative 2. So this is going to be a left-hand integral, or limit, and this will be from negative 3 up to c of 1 over x plus 2 dx. And then for this last one, the -2 is bad as well. So we'll want to limit as well, but this time the c is going to be approaching -2 from the right-hand side because we're coming from the right if we're looking at -2 to 0. So this will be from c up to 0. Now each of these antiderivatives is the same value. They're all going to be ln's. This is stuff prime over stuff. So for each of these, we're going to be using the ln of the absolute value of x plus 2. We're just using different bounds for each one. Okay. Now, the other thing to keep in mind here, when you're doing a problem like this where you've had to break up your interval at some sort of middle point, then what we said earlier in our definitions is that if you break up an interval like this into 2 or more pieces, if any single one of these smaller pieces or smaller integrals diverges, then the whole thing diverges. If any one of them does. So if I can find one of these that fails, then the whole thing fails. So if we look at this first one, when I plug in that upper bound, -3 plus 2 is -1, but it's an absolute value, so it turns into +1, and the ln of 1 is 0. So that's just going to be a 0. And then we're going to subtract from it the limit as a goes to -infinity of the ln of a plus 2. So let's think about what that does. -infinity plus 2 is -infinity, but it's an absolute value. So this is acting like the ln of +infinity, and ln of infinity is still infinite. So this goes to infinity, which means this piece fails to work. So automatically I can just stop and say that this original integral must diverge because one of these limits did not exist. And in fact, all of these are not going to work because if you look at -2 plus 2, that goes to 0, and ln of 0 goes to -infinity as well. So this would go to infinity, this would go to infinity also. But as soon as you get one that goes to infinity, you can stop. All right? Now the next thing that we're going to talk about is a really powerful tool. It's called a comparison test for integrals. It says that if you have two functions where f of x is greater than or equal to 0 and f of x is less than or equal to g of x. So think of f of x as the smaller function and think of g of x as the bigger function on some interval a to infinity. Then if you know that the bigger function has an integral, that converges, then the integral of the smaller function must also converge. Similarly, if the integral of the smaller function diverges, then the integral of the bigger function must also diverge. So this is a really nice thing to know about because sometimes our integrals are really tough to evaluate, but if you can compare them to an integral that is fairly easy to evaluate and you know whether or not it converges or diverges, then that tells you something about the one you want to know. So again, the test here says that if your bigger one converges, that forces your smaller one to converge as well. Or if your smaller one you know diverges, then that forces your bigger one to have to diverge also. So let's practice this. Suppose that I want to find the integral from 2 to infinity of 2 cosine squared x over x squared plus 4 dx. Now that would be a tough antiderivative to figure out because of that cosine squared x. This doesn't look like any of the techniques that we know how to integrate because it mixes those trigonometric functions with this fractional or rational function. So that's a tough one to deal with. So what we're going to try to do is compare this integral to an easier one that we do know how to integrate. And the way we're going to do that is we're going to use what we know about trigonometric functions, namely the cosine function. We know that cosine always is bounded between -1 and 1 because it oscillates between -1 and 1. So what must cosine squared be bounded by? Well, it's always positive because it's squared, so it's always greater than or equal to 0. and it can't get any larger than 1 because cosine of x is never larger than 1. So cosine squared of x is bounded between 0 and 1, which means if I multiply everything here by positive 2, that doesn't change the direction of the inequalities because we're multiplying through by a positive. And if I divide through by x squared plus 4, that does not flip any of my inequalities either because x squared is positive, and when I add 4 to that, that's going to stay positive. So I'm dividing by a positive value. So what this tells me is that 2 times 0 over x squared plus 4, which is still going to be 0, must be less than or equal to 2 cosine squared x over x squared plus 4, which is less than or equal to 2 over x squared plus 4. So think of this one as your greater function and this as your lesser function. So if we can show that this bigger function converges, then that would force this smaller one to have to converge as well. So let's look at this one a little more closely. And I want to look at it from 2 to infinity. So let's see if we can figure out whether or not this integral converges or diverges. First of all, let me change my infinite bound here to a limit. So I'm going to make this the limit as b goes to infinity of the interval from 2 to b. I'm going to take this 2 and I'm going to pull it out. So this is 1 over x squared plus 4 dx. Now that is our rule that you guys need to have memorized. That's an arctangent right there. And we do have an a squared. So the a would be a 2. And the antiderivative formula for this is going to be 1 over a arctangent of x over a. So that'll be 1 over 2 arctangent of x over 2. And that 1 over 2 is being multiplied by this 2 out front. And then we have our limit, and we have our bounds. So the 2's cancel. If I plug in our b here, we're going to get inverse tangent of b over 2. And if I plug in my 2, I'm going to get the inverse tangent of 2 over 2, or the inverse tangent of 1. Think about that one for a moment. What angle, when you take the tangent of it, gives you 1? Well, that's pi over 4, since sine of pi over 4 equals cosine of pi over 4. So when you divide them, you'll get 1. And then over here, we did this earlier today. What angle, when you take the tangent of it, is going to give you infinity? Because when I plug in b going to infinity, this is acting like the inverse tangent of infinity. So what angle, when you take the tangent of it, gives you infinity? That's positive pi over 2. So pi over 2 minus pi over 4 is positive pi over 4, which all we really care about is the fact that that's a finite value, which means that this converges. So since the bigger integral from 2 to infinity of 2 over x squared plus 4 dx, since that converges, and that is bigger than the one we're interested in from 2 to infinity of 2 cosine squared x dx over x squared plus 4. Since this is smaller, it's forced to converge as well. So therefore, this integral that we want to know about must converge also by the comparison test. Okay? So let's try this again for another example. This time we want to test the divergence or convergence of this integral here from 1 to infinity of x squared plus 3x over x cubed minus 4x plus 5. So what we want to do is figure out whether or not this diverges or converges, and obviously this is not a nice one to be able to integrate directly because it is this really yucky rational function. The only real strategy that we have to deal with something like this would potentially be partial fractions, but that would require that this denominator factor, and that doesn't look like it factors to me. So this is not something I would know how to integrate. So my idea here is to compare it to something pretty simple that I do know how to integrate. And what you can do to figure that out is since these x's are going to infinity, we're looking at this from the interval from 1 to infinity, think about what this is going to act like as x gets really, really large. Well, as x gets really big, it's going to be dominated by its dominant terms, which is an x squared over an x cubed, which reduces to a 1 over x. So the idea here is that we want to compare 1 to infinity of x squared plus 3x over x cubed minus 4x plus 5 dx. We're going to compare that to a much simpler integral, 1 over x dx. Now, ideally, if you remember from earlier on in this lecture, you remember that this one actually diverges. So if we know that this one diverges, then ideally we would like this one to be bigger than it, because if the smaller one diverges, that would force the bigger one to diverge. So we're hoping that this relationship is that this integral here, or this function here, is greater than or equal to 1 over x. So to check that, since this isn't really that obvious, you can check it on a calculator. So here's what I do. I just plug in y sub 1, that first yucky function, and in y sub 2 I plug in the simpler function 1 over x. And then what I'm going to look at are my tables. So if you go to your table set, you probably just want to start your table at 1 and go up by 1. So change in table here should be 1 as well. And then we're going to look at our table. And this first column for y1, that's our yucky function, and y2 is the simpler function. And what we want to notice is that all these y values for the yucky function are bigger than the values for the simpler function. And if you continue down, as x gets bigger and bigger and bigger and bigger, you can go as far as you like to convince yourself that that's going to continue to be the case. So the x squared over x cubed function is greater than or equal to the smaller one. So this is true, and you can verify that by using your calculator and using tables or graphs. So if we know that this one diverges, and I'll just prove it to you one more time in case you forgot, you can prove it by changing this to a b, taking the limit from 1 to b of 1 over x dx. The integral of 1 over x is ln of x. And when you plug in your bounds, that's going to give you the ln of b minus the ln of 1, which is 0. And if b is going to infinity, the ln of infinity is infinite. So this is infinity, which means this is going to infinity, so something larger than that must also be going to infinity. So by the comparison test, one to infinity of x squared plus 3x over x cubed minus 4x plus 5 dx must diverge, since the integral from 1 to infinity of 1 over x dx diverges. Okay? Now in the next example, we're going to look at something called Gabriels Horn. This is a region created by taking the curve 1 over x, with x being greater than or equal to 1, and the x-axis, so that region, and we're going to revolve it around the x-axis. So let's draw a picture of what this looks like. You get this 1 over x, which just looks like this, and 1 for x would just be that vertical line right there. And we're going to take this as x gets bigger and bigger and bigger, and we're going to rotate this region around the x-axis. So when I flip this over, the mirror image is going to look like this. So this is called Gabriels Horn. It has that horn shape to it. And we're finding this volume inside. Okay? So how would we go about finding this volume? Well, this is a nice solid volume inside of here. So if you take a cross-section perpendicular to the axis of revolution, it's going to have this nice disc shape. So we can use the disc method here. So that requires finding this center point and this edge point so that we can find that radius function. Both of these share the same x value. The lower point is on the x-axis, so its y value is 0, and the upper point is on our curve, which is 1 over x. So our radius function is just going to be the upper y value minus the lower y value, so 1 over x minus 0 is just 1 over x. So our volume formula for disks is pi times the integral from 1 to infinity of our r squared, so 1 over x squared dx. So because we have this infinite bound here, let's put in our limit. We're going to take the limit as b goes to infinity of pi times the integral from 1 to b, and 1 over x quantity squared is like an x to the negative 2. So when I integrate that and I add 1 to the power, that's going to give me an x to the negative 1 over negative 1, which is the same as negative 1 over x from 1 to b. I have that pi out front and I have this limit out front. So when I plug in b on top, this is going to be pi times negative 1 over b minus, when I plug in 1, I'm going to get pi times negative 1. B goes to infinity, so this is going to infinity. 1 over something infinite goes to 0. So this is going to be 0 minus pi times negative 1, which becomes plus pi. So we get pi for an answer, and that means that this shape, this Gabriels horn, has a finite volume, and its volume is just pi, which is kind of interesting. Now what we're going to do with the same region is, instead of talking about its volume, let's talk about its surface area. We just showed that it has a finite volume, so you would think that its surface area should be finite as well. So let's verify that, whether or not that's true. So remember the formula for surface area. Surface area is 2 pi times your integral of your radius function times the square root of 1 plus your derivative squared. So my radius function is that same 1 over x that we got up above. My bounds are still 1 to infinity. And then for my radius function, or excuse me, my derivative function, my original function was 1 over x, so that's the same as x to the negative 1, which means f prime of x is going to be negative x to the negative 2, or negative 1 over x squared. So that's what I want to put in here, and I want to square it. So this becomes 2 pi times the integral from 1 to infinity of 1 over x square root of 1 plus 1 over x to the 4th dx. Now to actually evaluate that integral, to find that antiderivative, is kind of hard to do, and surface area integrals tend to be hard ones to do because of that square root that shows up in there. So this isn't something that I really want to have to figure out how to integrate. So let's see if we can try a comparison test again. What I want you to notice is that x to the 4th is positive, so 1 over x to the 4th is positive. So 1 plus x to the 4th is positive, and if I take the positive square root of that, that is positive. And it's got to be greater than 1, because this 1 in here means we're adding something positive to 1 every time. So the square root of that has got to be bigger than 1 as well. So we know that that relationship is true. If I multiply both sides of this inequality by a 1 over x, then this gives me 1 over x times this square root on the left side is greater than 1 times 1 over x, which is 1 over x. The inequality won't flip here because the x's that we're looking at are positive x's when we go from 1 to infinity. So we're multiplying by positives, so the inequality stays the same. So this relationship is true. So if I want the area integral from 1 to infinity of both sides, this one we already know diverges. We've done that several times now. So this is infinite. And this one, which is the one we want to know, is greater than something that we know is infinite, so it must be infinite as well, which means it must diverge as well. So by the comparison test, this surface area, which is this 2 pi integral from 1 to infinity of 1 over x squared of 1 plus 1 over x to the fourth dx, diverges and is infinite. Okay? Which means that our surface area is infinite despite the fact that we had finite volume. So this is kind of a contradiction. Doesn't seem to make sense, but we just proved that it was the case. You can have finite volume and yet have infinite surface area. And this Gabriels horn is an example of that. All right, for our last example here, we want to do a proof. We want to prove that the integral from 1 to infinity of dx over x to the p either diverges if p is less than or equal to 1, or converges to 1 over p minus 1 if p is greater than 0, or p is greater than 1. So let's look at the p equal to 1 case first. If p is equal to 1, then this is just the integral from 1 to infinity of dx over x, since p is 1. And we've already shown in the last example and in the very first example we did that this diverges. So that's this equal to 1 case. So we already know that that's true. So now let's investigate what happens if p is greater than 1 and p is less than 1. So we're going to assume that p is not 1 from this point on. So that means this integral that we're looking at is the integral from 1 to infinity of dx over x to the p, and that has an infinite bound. So let's change this to the limit as b goes to infinity from 1 to b, and I'm going to change 1 over x to the p to x to the negative p dx. So this antiderivative becomes x to the negative p plus 1. You add 1 to the power, and then you divide by the new power. If I substitute in my bounds, this becomes the limit as b goes to infinity of b to the negative p plus 1 over negative p plus 1 minus 1 raised to a power. We're assuming that power is not 0 here because p is not 1, so we're not dividing by 0. We don't have to worry about that. And 1 raised to anything is going to stay 1. So we get that for our lower bound. And just to make it a little bit cleaner looking, let's go ahead and swap the order here of this addition. So instead of writing it as negative p plus 1, let's write this as 1 minus p. Okay, so this is what we get. Now at this point, in order to evaluate this limit, we need to investigate more closely whether p is greater than 1 or less than 1. So let's break this up into our two cases. So if p is greater than 1, then if you subtract p to the right-hand side, that means 1 minus p is less than 0. So 1 minus p is negative. So that means this power right here is a negative power. So when I go to take the limit of this b, this is b raised to a negative value. So this is an infinity raised to a negative value, and infinity raised to a negative is like 1 over infinity, and 1 over something infinite goes to 0. So that means this limit is going to go to 0, but we have subtracted from that 1 over 1 minus p still. So the limit part goes to 0. The bound at 1 went to this 1 over 1 minus p, and if we distribute that negative to the bottom and switch the order around, this just becomes 1 over p minus 1. So if p is greater than 1, then this converges, and what it converges to is 1 over p minus 1. So now let's see what happens if p is less than 1. So if p is less than 1 and I subtract p over to the right-hand side here, then that means 1 minus p is greater than 0. So 1 minus p is positive. So that means this limit that we're trying to calculate, the limit as b goes to infinity of b to the 1 minus p over 1 minus p, this power is now something positive. So this is acting like an infinity for this base raised to a positive exponent. So this is going to stay infinite minus that lower bound. But infinity minus a constant is still infinite, which means this diverges and goes to infinity if p is less than 1. So the difference between these two is if p is greater than 1, this limit goes to 0, and so we get a finite value. And if p is if p is less than 1, then this limit goes to infinity, and so we get infinity for our answer, which means it diverges. So putting it all together, if p was greater than 1, it converged to 1 over p minus 1, and if p was less than or equal to 1, we got the divergent case. Okay? All right, that concludes our video lecture on improper integrals. Good luck.